Can you guys hear me and see the screen?
Yes, sir.
Okay. So, hi everyone. This is Arpit. I'm a student at ISC and I'm your TA for this course, Introduction to Biostatistics. And today we'll cover topics that were taught in week 3 of the lecture. So here are some important links as always. First is the link for the live session. The next is for the link of the channel where the recordings of the live session are updated. And the third is the link for the Google Drive where these PPTs you'll find. So we'll get started with practice assignment number 3. Before that, does anyone have any doubts or questions regarding last class stuff or anything that was taught this week? So the first question is, if the scatter plot of variables x and y has a positive slope, the correlation between the variables is A negative, B positive, C no correlation, or D perfectly positive. So we had said that the scatter plot of two variables x and y has a positive slope. So it's something like this. Here. So the correlation would be positive, right? Because it is as x is increasing, y is also increasing. It will be positive. So we'll say it's perfectly positive when this correlation will be 1. So when the value of correlation coefficient will be 1, when it is perfectly correlated. So as much, so a amount of increase in x causes a amount of increase in y. So in that case, they're perfectly correlated. Okay. So the next question is, correlation coefficient lies between A 0 to +1, B -1 to 0, C 0 to infinity, and D -1 to +1. So the answer here is -1 to +1 because the correlation coefficient for any two variables, if you plot, let's say x and y. So the correlation between them can either be negative, positive, or there can be no correlation. So the value of this correlation coefficient will lie between -1 to 1. Right. So -1 is when it's perfectly uncorrelated, like negatively correlated, and +1 is when it's perfectly positively correlated. The third question is, the correlation coefficient R x of y is given as, we are given 4 options. So the correct answer here will be option C. So this is the formula for the correlation coefficient. So R is equal to covariance of x and y divided by standard deviation of x into standard deviation of y. Right. So which of the following statements is incorrect? A, extrapolation is used to determine a value outside of a given data set. B, interpolation is used to determine a value lying within a given range of points. C, extrapolation cannot be used to predict past values. D, interpolation is a useful tool in forecasting and predicting trend. So we'll look at the statements one by one. So we are asked to find which of the following is incorrect. So A, extrapolation is used to determine a value outside a given data set. Yes, that's why we use extrapolation. So in general, if we have some two variables that we are measuring, X and Y. And we basically have some experiment that we have done. Because of that, we know how the relationship is between X and Y at this point, right? So is it linearly increasing, decreasing, or something? So based on like some experiment, some data that we get, let's say we get this slide. So interpolation is basically when we are trying to predict points in between. So for example, we might have done an experiment at x0 and x, let's say 1, and some in 0.5, some in 0.75. But now let's say we wanted to know what is the value of y when if we would have ran an experiment with 0.6, right? So in that case, what we try to do is we try to uh, fit a line through the data that we already have and basically see what that line predicts for this point specifically. So that is interpolation. So you're trying to see inside the range of all the data that you collected by your experiments, how are other points lying down? Like what are the values for other points? But extrapolation is basically when you try to predict outside the range. So we don't know if this curve, so we don't have any data, let's say above the value of 1. So we don't know how the curve behaves after 1, right? So it can be linear, it can keep on increasing, it can saturate after a point, right? So we can fit a linear model here and try to make predictions here, but there's more chance that we'll have more errors in our predictions, but still we can make those errors if for good reason we know that this model is supposed to behave as linear, or let's say supposed to stabilize after a point. So we know and we can model those kinds of things and make predictions. So that is basically extrapolation. So that's when you're trying to predict outside of your data range. So outside of whatever range you did your experiments on, right? So it can be either positive or negative. So either direction. So based on that, extrapolation is used to determine a value outside a given data set. That is a correct statement. Interpolation is used to determine a value lying within a given range of points. That is also correct. Extrapolation cannot be used to predict past values. That is incorrect. Right. Yeah. Thought it was can. Right. Uh, okay. So this statement is also extrapolation cannot be used to. This statement is incorrect because extrapolation can be used to predict in a limited sense, as in like if X is a time variable, then we can use extrapolation to predict back in time, but those might be more incorrect. But yeah, so we'll go ahead with saying that this is also incorrect. This is incorrect, yeah. And the interpolation is a useful tool in forecasting and predicting time. That is also incorrect because interpolation, as I said, is used when you know within your data range what is supposed to be done. Right. It's not forecasting anything into the future, or it's not predicting time outside of the data. Right. So the answer here will be C and D. Question number 5. Calculate the correlation coefficient for the given data set. So we are given that what is the amount of fertilizer added in liters and what is the yield of crop, kg per hectare. It's straightforward. You have to calculate the correlation coefficient. So again, here we'll use the formula. So as I said before, the formula for correlation coefficient of X and Y is given as covariance of x and y divided by standard deviation of x into standard deviation of y. So if we write it out, what we'll basically get is xi minus x minus y summation of this divided by n minus 1. So this is the covariance of x and y. Right. And this will be divided by standard deviation of x is xi minus x bar square divided by n minus 1 total. And similarly for y we have so here since we have root n minus 1 into root n minus 1, it will be n minus 1 and we have n minus 1 here. But so what we essentially get is right. So this is the formula that we get, but since we are using data like this, so we have values of x and y, we can get away with calculating the mean of x and mean of y and basically remove a lot of unnecessary calculations by simplifying this equation, and which basically it simplifies to this. Okay, so in this formula, we don't have to use the calculate the means for x and y. So it will be easier for us and less and easier calculations for us. So we'll be using this formula to calculate the correlation coefficient. If you guys want to see how this is derived, we can also do that sometime later today. Yeah, how this formula simplifies to the other one. But this is the formula that we'll be using for today. And like, yeah, to make our calculations easier. So what we have here is we have xi and we have yi. So our xi is 1, 2, 3, 4. So what we need here is xi yi. We need summation of xi yi, summation of xi, summation of yi, and summation of xi square, and summation of yi square. So we'll just make columns for all of that. So we have x. We have xi square. And then we have y, y square. Right. So xi yi here will be right. So now we have all the elements that we need to make the calculation. So we'll just sum all of this. So this will be our summation xi, which will be equal to 10. Xi, right? Ah, okay. So the correlation coefficient R is equal to n into summation xi yi minus summation xi summation yi divided by summation xi square minus n summation in the same time. This will be so n here is 4 since we have 4 data points. Right. So we have 66.2 and 26.2. Get 4 into 10 minus 10 square. Okay, so we'll use a calculator. And I'm just doing the calculations using a calculator. So this will be 20.8 divided by 4.472 into 8.7, which will be 22.8 divided by 23.646 is approximately equal to 0.96. So the answer here will be option A, 0.96. Does anyone have any doubts or questions? One day I'll also look up how to use the online calculator and maybe we can talk about that also. I don't know how easy or difficult it is for you. We'll check it out. Yeah. So what we do is basically we take xi, we take yi, we calculate xi, yi, then xi square, then yi square. And all we have to do is just sum all this up. We don't need to calculate any means or standard deviation or anything. Then we just plug it into this formula and we basically get our value. A student performed a Bradford assay to determine the protein concentration of an unknown sample. She constructed a standard curve using increasing concentration of BSA protein and plotted points on a graph where absorbance was given on y-axis and protein concentration was given on x-axis. The equation of this line is y is equal to 0.05x plus 0.007. The unknown sample gave an absorbance value of 0.557. What is the protein concentration of the sample? Just a brief background on what a Bradford assay is and what they do basically is. So if they have a protein for which they don't know the concentration, so or a solution for which they don't know the concentration and they want to put a protein in it, so what they'll do is basically they'll run an assay where basically they'll use this BSA protein or bovine serum albumin. And for known concentrations of this protein in a solution, they'll basically plot what is the uh, absorbance or the optical optical density or the absorbance value. Right. So then you get a curve like this after you make these observations. So if you have an unknown protein for which you know what is the absorbance because that is what you measured. So you have a value of y. What you want to know is basically what is the value of x, given that x is concentration and y is absorbance. So that's what we'll be doing. So we have this equation of line, which is y is equal to 0.05x plus 0.007. We are given the value of y, which is y is equal to 0.557. What we want to find is the value of x. So we'll just first rearrange this equation. So we'll subtract 0.007 on both sides. We'll have 0.05x is equal to and then we can just divide it by 0.005. So right. And now we know that y is equal to 0.557. So x will basically be equal to 0.557 minus. So there will be option B 11. Okay. So the next question is, a research study recorded the time taken in y seconds to obtain absorbance x as given below. Calculate the coefficient of correlation. Again, we are given some data. We'll take in this case X as time and Y will be absorbance. So what we have here is basically Xi, Yi, and to calculate the correlation coefficient, we need Xi, Yi, we need Xi square, and we need Yi square. Right. So 0 to 60. Yeah. So what we need to do is first calculate. So Xi square is easy. 0. Yeah. Then Xi Yi will be yeah. So then we'll sum all of it up. And okay. So we are asked to calculate the coefficient of correlation. So in this case, R is given as n into summation of Xi I minus summation of Xi summation of Yi divided by n into summation of Xi square minus summation of Xi square n by I. Right. So we'll just input the values. N here will be 7 since we have 0 to 6, 7 data points. And we'll have here this 7 into 94.8 minus 9210. second. Answer here will be option D, 0.97. So again, what we did was we took xi, we took yi, we calculated xi, yi, we calculated xi square, we calculated yi square, and then we basically took the sum of all of it and we put it into this formula. Given covariance of xy is 28 and variance of x is 16, variance of y is 81, find the correlation coefficient. So here we'll use the other formula. So R is given as covariance of x and y divided by sigma x, sigma y. So we are given sigma square. So what we'll just do here is covariance is 28. So we'll just take the root over. So it's basically like this. So we have 28 which is so you can just put this 7, 9, excellent. So answer will be option B, 0.778. A coin is tossed twice. What is the probability of getting two heads? So if a coin is tossed twice, so we have talked about sample space, which is all the events that can occur. So let's say we are saying that if a head occurs, I'll write heads. If a tail occurs, I'll write tail. So if we are tossing a coin twice, so we might have a heads and a heads, or we might have a heads and a tails. We can also have a tails followed by a heads. or we can have a tails followed by a tails. So these are all the possible combinations that can happen. So this is our sample space. So if you toss a coin, according to the rules of probability, we know that probability of sample space will be equal to 1. So the probability of this happening is 1. So any of this will happen because this is the sample space. So the total area, total thing. So, okay, so we are given what is the probability of getting 2 hits. So let's say we have an event, which is basically the probability of, which is called getting 2 hits. Right. So this will be a subsample of the sample space, and this will basically be this because we are getting 2 hits. So this is the only event in which it is occurring, only case in the sample space where this is occurring, right? So the probability of E is basically given as number of items in E by number of items in S. So number of observations in which the event happens divided by total number of observations. So what we'll have is 1 divided by 4, which is 1 by 4. So the answer here will be option C, 1 by 4. If R is equal to -1, the correlation between the variables is perfectly positive, perfectly negative, positive, 0. So the answer here will be perfectly negative because R equal to -1 means it's perfectly negative. And +1 means it's perfectly positive. So like it's basically a linear relationship. Number 11. If the correlation coefficient between two variables is 0, which of the following is true? So option A, there is no linear relationship between the variables. B, there is perfect linear relationship. This is false. If there's linear relationship, it would have been 1. Right. Perfect linear के लिए a perfect linear positive is +1. Perfect linear negative is -1. So 0 is not this. The variables are independent. This is also incorrect because the variables might be dependent even when the correlation coefficient is 0. I'll just show you. The scatter plot will show a perfect line. It will not show a perfect line because there is no linear relationship. So the answer here will be option A, which is true, which is there is no linear relationship between the variables. So what I mean is, so we have X and Y. And if we have points like this, that means they are correlated because they seem to be falling along this line, right? However, if so that thing can be like this or can be like this, right? So if the variables are independent, so they're just scattered all around, in that case, you will get a 0 correlation. You won't get a relationship, right? So correlation will be 0 if X and Y are independent. If X and Y are independent, right? But the reverse is not true because there might be cases like this. For example, we have X and Y, and let's say our points are distributed somewhat like this. So in this case also, if you take a, what do you say? Uh, if you calculate the correlation, it will turn out to be 0 because if you take the mean and you basically take the distances from the mean, it will cancel out on each direction, right? So the correlation again will be 0, but X and Y are not independent here. right? Because you can see there is a relationship between x and y, and this would be a relationship of a circle where x square plus y square equal to 1, or c, or some form of this, right? X square plus b square equals some form of this is something uh, that is a relationship between x and y. But the correlation is zero because there's no linear relationship between x and y. So if there is no linear relationship between them, then only the correlation will be zero. Right? Not then only, but then the correlation will be zero. Then question number 12, which of the following values of R indicates strongest linear relationship? So we have minus 0.95, 0.85, 0.4, and minus 0.65. So the answer here will be A, minus 0.95, because when we are asked what is indicates the strongest linear relationship, we are just looking at the value and not the direction, right? We are not thinking if it's positive or negative. So minus 0.95 is the strongest linear relationship because it's as close to minus 1. So if your value is close to minus 1 or 1, it gets stronger. If it is close to 0, it's a weak relationship. The regression line equation is y is equal to 3x plus 5. What is the predicted value of y when x is equal to 4? So this is a straightforward question. We have y is equal to 3x plus 5. We have x equal to 4. You just plug it in. So 3 into 4 plus 5 is 12 plus 5, which is 17. Answer here will be option A, 17. Right. Next question is, which of the following statements is true? Interpolation always gives more accurate predictions than extrapolation. Extrapolation can be more reliable than interpolation. Interpolation is used only for predicting future values. Extrapolation is always correct if data is linear. So option D is false. Extrapolation is not always correct if data is linear. It has a certain error that is associated with it because we are predicting outside of the range of our data. We are more or less speculating in a way. Right. Interpolation is used for predicting future values. That is wrong. Interpolation is used to predict values that are in between your data, not future or past. Extrapolation can be more reliable than interpolation. This is also false. Extrapolation is less reliable because we are more speculating, and interpolation, we know what is the relationship that is being followed across this range, right? So option A, interpolation always gives a more accurate prediction than extrapolation. That is the correct option. So the correct statement. So the answer here will be option A. Right. 15. A data set has covariance of 12 and standard deviation of x is 3, standard deviation of y is 4. What is the correlation coefficient? So correlation coefficient is given as covariance of x and y divided by sigma x into sigma y. We are directly given these values. So it's 12 divided by 3 into 4. It's 12 by 12, which is what? Answer here will be option A. So this is a perfectly linear relationship. Okay. A nonlinear model is best suited for data that shows a straight line trend in a scatter plot. No, if it shows a straight line trend in a scatter plot. So if you have data like this, it might be following a linear relationship. It might not be nonlinear. It might just be like this. Right. Has a constant rate of change. This is also false because linear relationships have constant rate of change, which is called the slope. It's a constant rate of change. So at any of these points, if you take out yi minus y1 minus y2 by x1 minus x2, it will be the same, right? If it's a line. So it has a constant rate of change. So if a non-linear model is not suited for that data, shows curvature or changing slope. So if you have data like this, where basically the optimal line might look somewhat like this, where the curvature or the slope is changing, then you should consider a non-linear model. Has a correlation coefficient of 1. Again, this is wrong because correlation coefficient of 1 or -1 indicates a perfectly linear relationship. So it will either be something like this or something like this, and a linear model is suited for it. So the answer here will be option C, shows curvature or changing slope. Question 17. The probability of event A is 0.4 and event B is 0.5. If A and B are independent, what is the probability of A and B happening together? So A intersection B. So we are given that probability of A is 0.4, probability of B is 0.5. And we have said that A and B are independent. So what that means is if A happens, it does not affect the probability of B happening. And similarly, if B happens, it does not affect the probability of A happening. But so in cases of independent events, what we know is if you have n independent events, let's say A1, A2, A3, an, and you want to look at the intersection of that, right? So if you have n independent events, and so all of them are independent of each other, so probability of one of them happening does not affect the probability of anything else, any other thing happening, right? So the most common example that you can think of is like tossing a coin multiple times. So each time you toss, if you count it as an event, right? If you, what do you say? So getting heads at each coin toss, if that is an event, so getting heads for the first toss, getting heads for the second toss, third toss, and so on and so forth. So all these events will be basically independent of each other because even if you get a heads in the first toss, it does not affect you getting a heads or a tails in the next toss, right? Those are two independent coin tosses. So if you have, if you want to calculate this, so intersection is basically when we want to calculate probability of both the events or multiple events happening together. So this is probability of event A1, A2, A3 till AN, all of them happening, is basically equal to probability of A1 into probability of A2 into probability of A3 into probability of AN. So in this case, we have that scenario where basically we are asked what is the probability of A intersection B. And we know that A and B are independent. So just probability of A into probability of B is 0.4 into. So the option is 0.2. A fair die is rolled once. What is the probability of getting a number greater than 4 or an even number? Right. So again, here we can say that our sample space is 1, 2, 3, 4, 5, 6, because the dice is rolled only once. Right. We can get either in any one of these values. So we are asked to find the probability of getting a number greater than 4 or an even number. So this or here indicates that there are two events that we are looking at. Okay. So first is getting a number greater than 4. So let's say our event 1 is getting a number greater than 4. So our E1 will basically be 5 and 6. two numbers can satisfy this condition if we get it in the dice roll. And a second event, the one that comes after the OR, is getting an even number. So E2 will be 2, 4, and 6 because all these three numbers are even, right? So what is the probability of getting a number greater than 4 or an even number? So that or indicates we are looking at union, right? So probability of E1 union E2. So I talked about this. So basically, when we are talking about probabilities, a brief introduction is this is using Venn diagrams, how we can represent things, right? So this is our S, which is our sample space, where we have all the rolls of the dice, 1, 2, 3, 4, 5, 6. This is our event 1, which is basically getting a number greater than 4. So we have 5 here, we have 6 here, right? Then we have our event 2, which is getting an even number. So we have 2, 4 here, and we have 1 and 3 outside somewhere, right? So E1 is basically that small circle, E2 is basically that large circle that we see. And so E1 union E2 is basically this shaded region. If it's easier for you, you can just create Venn diagrams like this and make the calculation. So here we have 1, 2, 3, 4, 4 numbers, and in total we have 6 numbers. So it will be 4 by 6 or 2 by 3, right? But if you want to basically put in formulas and all, also we can do that. So we have it is probability of E1. So probability of E1 union E2, which is the shaded region, will be probability of E1, which is this, plus probability of E2, which is this, minus probability of this middle region. Because notice this region is present here and this is also present here. So this we are counting twice. So we need to subtract that once, right? So this is probability of A. This is, sorry, E1. This probability of E2. And this is probability of E1 intersection E2. So both of them happening together, right? Because that's the common area, common place. So minus probability of A E1 intersection E2. So we have probability of E1 is 6. E2 is 3 by 6 minus A intersection. So this will be E1 intersection E2, which will basically be 6. We have 1 by 6. This 5 minus 1, 4 by 6, which is 2 by 3. Again, which we just calculated here by counting numbers. Right. In probability, the set of all possible outcomes of an experiment is called, so we know the answer is B, sample space. So event space is basically when you have some event that you are seeing. So for example, here E1 is the event of getting a number greater than 4, our event spaces 5 and 6, because those are the observations. Those are the rolls of the dice, which makes, which is basically the event which makes the event happen, right? And sample space is collection of all the events that can occur due to the experiment or the probability, or the task, right? Question number 20. If PA is equal to 0.6 and PB is equal to 0.5 and PA union B is equal to 0.9, what is PA intersection B? So you know the formula for PA union B, which we just talked about, which is PA intersection B. What we are given is we are given PA, we are given PB, we are given PA union B. We are asked what is this? So PA intersection B is equal to, if we bring it here and bring this here, okay. Yeah. So that's all 20 questions we had for today. If you guys want, we can move through this derivation for this formula. Other than that, if you guys have any other doubts or questions, we can uh, feel free to ask or write out in the chat, whatever feels comfortable. Okay, so basically, once we have this formula, I'll just explain like how this turns into this. We can basically expand it. So hmm. And then similarly for Y, we have So here basically this summation xi into y bar, we can take out y bar outside. So we'll do that. Xi y bar into summation xi minus x bar into summation yi. We'll take all the constants out. So plus, so the summation basically represents summation I is equal to 1 to n. We are assuming that n is the total number of data points we have for x and y. So if we take this x bar into y bar, the sum of that n number of times, so that is basically this. So we have n x bar y bar divided by xi square summation minus 2x bar summation xi plus x bar square. Again, so here if you see basically uh, summation xi will be equal to n into x bar, right? So if we have the mean, so x bar is basically the mean and x bar is given as summation xi by n, right? So to get summation of xi, we just need to multiply n here. So summation xi is equal to n into x bar. Similarly, summation yi is equal to n into y bar, right? So using these substitutions, we can get that here. This will be summation xi. This will turn into x bar, n into x bar, x bar into n. This will become y bar into n, right? Then here we'll have n into x bar, and here we'll have n into y bar, right? So then we basically have xi by I minus n x bar y bar minus n x bar y bar plus n x bar divided by c square minus 2n x bar square plus. And similarly, for the x bar square, this will again be n times. So we are just taking x bar, x square, x square, x square, x mean square, x mean square, x mean square n times. So this will again be n into x bar square, and this will be n into y bar square. Okay. N x bar square. Then this will be summation x square minus n by. Right. So here a lot of terms cancel out. This minus 2 and this minus 2 and this. So now we just have a single minus here. These two cancel out. So what we get is a much more simplified version. Here we'll go up. So what we have is Right. So here again, we can basically, so now we have a very simplified formula, which is in terms of the mean and xi, yi, and the mean of x and y, right? But notice that if we would have calculated our R square in this way, we would have the need to calculate mean of x, mean of y, right? Then the square of mean of x, square of mean of y, and again we would have to calculate xi square and yi square. Some people find this easier, so if you guys want, you can continue using this formula also. So there's a kind of an intermediate formula here. Right. Now, in this formula, so this is one formula, and in this formula, what we can do is basically to remove these mean terms, we can just substitute. So x bar will be equal to summation of xi by n. Y bar is equal to summation of yi by n. Then x. So now what happens is, now we have r is equal to xi yi summation minus n into summation of xi by n into summation of yi by n divided by xi square minus n into summation of xi by n whole square. And for y again, yi square minus n into summation of yi by n whole square. Again, what we see here is n cancel out, and then we have the square terms cancel out, right? So what we'll have is xi yi minus summation xi into summation yi divided by n xi square minus summation xi whole square divided by n. Right. So here what we can do is to take the n to the numerator in both the upper and lower terms. What we can do is we can multiply by n on both the upper and the lower side. So what we have is basically this formula. So n into xi yi minus, so this n and this n will cancel out. So we have summation xi into summation yi. Then again, this n we can write it as, instead of writing it as n, we can have root 10 here and root 10 here, which are multiplied. So this n will go inside the square root, and we have n into this term, and this root n and this root n will cancel out. So n into xi whole square, xi square minus xi summation whole square, and similarly for y. So this is the formula that we just used, right? So in this case, you see that there's no need to calculate terms like this mean, x bar, y bar, and x bar square, y bar square, right? But you have to calculate xi, yi, xi square, and yi square, summation of all that. And here again, you have to calculate summation of xi square, yi square, and summation of xi, yi. So you don't have to make any extra calculations here. Right, only summation of xi and summation of yi, which anyways you will probably calculate. But here you need to calculate the mean, so we use this formula. Okay, so yeah. Does anyone have any questions or doubts? Sorry if this was very long digression, but yeah. Okay. So we learned how to calculate the correlation coefficient, the formula for correlation coefficient. We learned about interpolation, extrapolation. We were calculating the correlation coefficient using the formula. So yeah, xi by a, xi into ya, xi square, yi square, summation of all that you plug into this formula. Then we learned how to basically calculate values of x given values of y in a line, and again correlation coefficient, then calculating correlation coefficient given different values, and then probability. Then again a bit about probability independent events. So take all outcomes. Okay. So let's say we are given something like say we are given rate, and we are basically asked we are given that there is a relationship between A and B, and you are given that the value of B is, let's say, 1, right? So what is the value of A for the best fit line? Let's say the best fit line is of this form. So what is the value of A given that the value of B is 1, and you are given the points x is equal to this and y is equal to 10? How would you try to solve this question? Can anyone answer? Okay, so Anshu says basically A is equal to y bar minus B into x bar. So you get it from this equation, you take it this side and you basically take the mean. Is that why are you taking the mean here? Like that is correct. But why do you think you're taking the mean here instead of like just trying to do it point by point? Hmm. So we know the value of B is 1. So A is given by y bar minus x bar. So what do you say? This whole equation basically comes when you try to minimize the least fitted squares, right? So what you do is, let's say you assume we have a line which basically predicts this best fit line. So the five, so we have this data like this, right? Okay, so we have uh, this data. So we are trying to find a best fit line. So we know the line is best fit if it minimizes these errors, right? So our line is of this form, y is equal to ax plus b, a plus bx, sorry, right? Uh, so these errors will basically be the values of yi minus the predicted values of y at the point, right? So yi minus a plus bxi, because this is basically formula for y predicted, right? So this, the square of this, and you basically sum it up for all the points. So this is the quantity we are trying to minimize. So to minimize this, we basically get its derivatives, partial derivatives. So this is a square error. Okay. Let's say error here. So we basically do this partial differential of d by dA and d by dB, and this will be equal to 0 at the point of uh, minimum. Right. So uh, that's when we'll find these values. So anyways, since we are given the value, so if you write these equations and simplify, it will come to somewhat like this. So since we are given the value of b is equal to 1, we can substitute 1 here. So a is equal to y bar minus x bar. So what we need to do is basically calculate y bar and x bar. So summation of x is equal to 1 plus 2 plus 3 plus 4 plus 5, 9, 12, 16, 50 by n. Again, like that is equal. So our A will be minus 1. So our best fit line would be of the form y is equal to minus 1 plus x. So y is equal to x minus 1. So if we mean this, properly. That line is basically rising. So a point line basically passes through two of the points and it's surrounded by it. Okay. Okay. Does anyone else have any questions or doubts? So if no one has any questions, I'll wait here for a few more minutes, 10 minutes, 10 to 15 minutes. And after that, we can stop. If anyone has any questions or doubts, we can discuss. Okay, so someone says question number 14. Which of the following statements is true? So, as we discussed, we'll talk about the incorrect ones first. So, extrapolation is always correct if data is linear. So, that is not true, right? Because your data that you currently collected, which gives you a line like this, let's say the trend overall is linear, right? So, this is the range in which you collected your data from A to B. So in this range, it is linear, and after this, you have extended. And let's say the data is linear going forward and going backward, but there might be some outlier at certain point, right? So you can never guarantee that the extrapolation is always correct if the data is linear, because there might be some outliers at some point. There might be something that might be happening at some point, right? So this is incorrect. Then interpolation is used for predicting future values. That is incorrect because in interpolation, you have collected all the data in this range. So there's nothing in the future that you are trying to predict, right? What we are doing is basically predicting in between and filling the gaps, right? Extrapolation can be more reliable than interpolation. Again, this is false because, as I mentioned before, if you do an experiment and you figure out that there's a linear relationship between point A to point B, for the variable x and y, it might not be that the relationship is linear here. Relationship might be different here, right? Most common example of this would be like species accumulation curves, right? So if you keep on sampling and number of species, you see that if you keep on sampling at a given area, if you keep on going to the same park and trying to look for new different kinds of species of birds or new different kinds of insects or other animals, mhm, what you'll basically find is overall this curve goes like this. Similarly, population growth curve uh, basically goes like this for an exponential case. When there's an exponential rise in population, for example, in bacterial colonies and all, right? Whereas we have curves like this, which are like sigmoid curves. which are followed in like more natural, larger animal populations, which are limited by size and resources and other kinds of things, right? So you have all these kinds of relationships in nature. So when you are basically making observations in nature, you cannot assume the relationship is always linear. It might be very complex, right? So in that case, extrapolation can never be as reliable as interpolation, because in interpolation, you know how much wrong you can be, right? So for example, in this range, you fitted a line and this is the maximum error that you are getting. You know that any value you interpolate will be less erroneous than this value with almost a very high certainty, right? But you can never put that bound for an extrapolation thing because you are not sure how off you will be. Option A is interpolation always gives more accurate prediction than extrapolation. This is true because you have collected the data in that range and you're making predictions in that range. So you're more likely to be correct. Right. More likely to be more accurate because you know that how the data behaves. So for example, let's say you have a magnet and let's say you heat it, right? So this is temperature and this is some form of magnetism you're measuring, right? How magnetic is it? And let's say you make your observations at in and around room temperature, 24 to 35 degrees Celsius, right? So in this range, you see that as the temperature increases, the magnetic property slightly decreases. It's a linear relationship. Right. So you took a lot of data points to arrive at this observation, right? So the line that you show in between what it is following is more likely to give you more accurate predictions because this line is best fit given that the data that you have collected, that you have actually measured. So you have measured across this range. So you have measured 28, let's say 30, 32, and so on and so forth, right? But now uh, we know that basically at higher temperatures, what happens is magnetism suddenly goes away. So it decreases, something like this. Right. So you cannot be sure about what you are extrapolating to here. If your linear line goes on like this, you might predict something which is very different than what is actually observed. Right. So extrapolation always is less accurate than interpolation and less believable than interpolation unless you have very strong ideas of how the curve is. For example, if I know this is a population growth curve or it's the inverted sigmoid kind of curve like this, I would be more sure of making predictions here and here because I will fit a sigmoid line into it, not a linear line, right? So answer here will be option A. Was that clear? Thank you. Okay, I'll wait for 10 more minutes. If there is any more questions, we can address that or we'll stop here today. And we are till 7:40. I'm here till 5 more minutes. If anyone has any doubts, feel free to ask. I'll turn off my mic and camera now. But I'm here, so like, yeah, you can ask in chat or unmute yourself. Okay, guys, we'll stop here. We'll meet again next week at the same time. Thank you for attending. Whatever was there. Yeah. Bye. Until next time.